Hello, everyone. Okay. So as usual, we'll start at around 11:10. In the meantime, if you had any questions, please send them into the chat.
Peripherals. So
Okay, let's start. As usual, please, if you can turn on your camera, do so. And I really hope more people will do it. So today, we're going to talk about control flow. But before we go into that, and can you hear me well? Just a sanity check. Can anyone type the answer? Can you guys hear me well? Okay. Okay, hope there are no lags anymore. Okay. So there's one important thing I want to cover today that's unrelated directly to this lecture is that we had several instances in the labs where the students came with the code fully functional, but were completely unaware on how it was done and how it works, and were not able to answer any questions. So please don't be surprised if you come with the labs and you didn't do it yourself and don't understand how it's done, then your grades can be severely deducted up to the half of the grade easily, right? So the goal is not to bring just the functional code. The code, we need to make sure that you understand what you're doing, right? You're not just borrow it from someone. So make sure you do understand everything you have and how you do it. Yes, you might talk to others about how to implement certain things, but at the end, everything needs to be done by yourself, and then you would be capable of answering all the questions. So any questions about that from you guys? Yeah, and I really hope at least some of you will turn on the camera. So I don't see anyone. Okay. Related things on their exam. So we are considering, I think I told you at the beginning, that the exam will be take home, but we consider that after we internally grade the exam, yeah, I don't know why, I just had several meetings and it was not lagging. I don't know what's happened with the internet. So can you guys hear me now well? Okay, sorry about this. So talking about the exam. So what we are considering doing and what most probably will do after you write your exam, we will take and grade all of those exams. And after that, we will have individual short one-on-ones with everyone. So if that happens, and then when this happens, what was going to happen is that we will give you back your okay, I'm talking about the exam right now, and what we're planning to do, and after the exam is graded, so you will do it at home, right? And you submit it to us, we will grade that exam, and then later on, what's gonna happen is that we're gonna meet, me and TA, with each of you, and we're gonna ask a few, questions for your exams, right? So the questions won't be on something random. The questions would be about the problems. It would be more for us to understand whether you understand what's written in your exam, right, essentially. So those will be short meetings. So if you do it all by yourself, that's not a problem at all, right? But, that's a way for us to understand that you're doing it by yourself. So again, you get enough time on your exam, please make sure to do the work by yourself. And we want to make sure that you actually learn something from this class. So we're not grading anyone harsh, right? But we want to make sure you're doing your own job. So it's better to have, the lab that's slightly, maybe not fully correct, but done by yourself, that having something you copied and correct from someone, and then you lose like a lot of marks just because you don't understand what it is. So David is asking, is it a typical 2-3 hour exam? So essentially exam would be a little bit shorter. So you don't have to write, like the whole exam would be more like 90 minutes exam, right? We just give a window so you don't need to start it at exactly the same minute, right? Because some people in different time zones, right? So we had a window. Within that window you need to start. You can use as much time of this 3 hours or 2 hours you want, right? So that's a window, and the exam would be 90 minutes. Most probably we'll time it, so you would have to finish, so you start, you have to finish it and submit, the file, right? So the way I expect it is you're gonna get the file, and then, there will be some multiple choice questions, some questions you would have to write down, and then you can send as a scan copy, either make a screenshots with your cell phone or scan it, whatever way you like, right? Those questions to us as like PDF or big image file, and then submit it as a file. So that's the way we anticipate it, because there's going to be, we're doing in quiz, as a practice, we do multiple choice question, but the most interesting questions has to be fully written, right? So that would allows us to see your logic, not just how you get the answer. Okay, so when we're going to grade, we're not grading just the correct answer, we're grading the logic. Like, for example, you might get a question about, here is a sequence of memory addresses that goes into the cache. What would be the cache behavior, right? I don't care about just the correct answer about hit miss rate. I would care about to see how you draw the cache and how you're going to go, like, which request you believe is a hit, which is a miss, right? So it's not only the final answer, we're gonna look at the intermediate results. So David, does it answer your question? Okay, any questions from anyone else? So is the exam open book, right? Well, like, I mean, it's a take-home exam, right? Like, you can do whatever you want. Like, we are not watching you, right? So so it's completely up to you. So the questions would be done this way so that you can use slides if you want, right? So it's but at the end of the day, most questions would be like, you cannot just directly Google them, right? You would have to do the work yourself. So the exam would be around 90 minutes. That's my plan right now, plus minus a little bit up and down. So after we write it, I will tell you the exact time, but you should roughly expect about 90 minutes exam. First, I'm not a big fan of super long exam, like 2-3 hours exams. So it's not, it's probably going to be around this ballpark, around 90 minutes. Yeah, there was a short lag again. At least right now when I see IV, at least I see there was a lag, so I know what to say. Anyway, let's start. Is there any other questions about exam or labs? Okay, let's start. So we're in week 9 right now. So we talk already a lot on the arithmetic thing, right? And we talk about storage for quite some time. So I guess you learned some advanced topic with me about DRAM and about cache that you typically don't learn in this course in such level of detail, but I hope you enjoy it and you understand your hardware a little bit better. Again, if some of you still confused or not sure how the caches work, please come with questions after the tutorial on Fridays, right? And ask your questions, right? I'm happy to go over that again. I know that was not an easy thing, but that's essentially how the caches works in the most primitive form. So hopefully, you learn it by the end of the day. So please don't be afraid if you feel like you're still not sure how it works. Tell me at the end of the tutorial and I answer questions. So today we are going to talk about controller thing. We are not going to do the most complicated things about it. We're going to talk about basics because there are more advanced things such as, branch predictors that we're not covering in this class that you need to cover in computer architecture classes. But essentially, this is the unit we're going to talk today. So essentially what we learned. So the arithmetic thing, and I hope you can see my mouse here, right? So the arithmetic thing tells you how to compute. It knows exactly how to do math. The storage things give us registers, memory. It gives us information to make operation on. Okay. Okay, can you guys hear me now? Yeah, so there is arithmetic things where you do all the computation, and there is a storage thing, right, that tells us where to take information to do math, additions, multiplications, all the other sophisticated computation requires having the data to manipulate on. But all of that one function if our unit doesn't know when to do and how to orchestrate things. And this is the controller thing. So the best way to think about control unit is this way. It's us ruling this thing, right? So the controller unit controls a so-called data flow of the execution that's usually called data path. So different executions are gonna have different data paths. So if you look at the graph or the flow of the computation, it might vary depending on what you're doing. And today we're gonna very meticulously gonna learn what you're gonna do step by step, okay? So can you guys hear me now? Like, is there any problem? Okay. So the data path of a processor is essentially a description, illustration of how the data flows between processor components during the execution of an operation. So whenever I'm going to tell you what is the data path of these instructions, what you need to describe is what is happening step by step and what certain values are written in certain registers and which values are equal to something. So essentially data path is a description, illustration of the process. In reality, the process happens kind of not instantaneous, but in a few cycles, the data is propagated. You can't show the continuous process. You just describe it step by step. So this is what data path is informally. So let me give you, again, an informal, simple example. Remember, this is not a real chip. This is a very, this is a huge simplification of what happens, but that should give you a feeling on what data path is. So in the most processors has stages shown the diagram. So essentially what happens, the processor doesn't do everything in one instant, in one cycle. What it does, it does stages. So for example, the typical processor has something called processor counter, or an address called PC. This is a pointer which instruction I want to execute next, okay? Okay, so that instruction, by this address, I can read this instruction, right, from the instruction memory. And then that instruction has the next steps on what to do. And in parallel, by reading this instruction in the first step, I also want to point the instruction pointer to the next instruction. So by default, it's just adding to the instruction 4 bytes plus 4, because the next instruction, it's the next 4 bytes. And we'll go carefully over that. So this is the typical stages that we have. So the first stage has a name. It's called instruction fetch, because it doesn't do really anything other than taking the address, reading the instruction memory, and giving us the instruction. That's why it's called instruction fetch. The second stage is called instruction decode and register fetch. As the name suggests, what we do in this stage, we take the instruction that, as you see in the next slide, is just a sequence of zeros and ones. It doesn't look any meaningful to you until you decode it. After you do decode, right, you would need to, so instruction uses registers, right, as we learned in the previous lecture. So we need to understand which registers it uses and try to get, ready to read those registers. We also might need to do something called sign extension. We'll see why this is needed, okay? And after that, after we get those registers, we need to max out the values that are needed to the LU. So remember, LU operates on only, like, say, 2 registers or 1 register. So we need to give the right values to LU, right? You need to resolve everything related to the addresses later on, right? because results of the LU can go into register or memory. So you see, so depending on where the result goes, it might go all the way to another register, right, back to the register file, or it might go all the way to the memory itself, right? So, so depending on where it goes, there can be different things. Okay, any questions? Okay, let me try to switch my internet connection. I feel like it happens because too many people are working from home, and no matter how much I talk to my internet provider, they cannot fix the problem. Okay. So I'll just context switch for a second to a different. So let me stop sharing. Okay, let's try to use my phone. So can you guys hear me well now? Let's see, where's the chat? Okay, so let me know if that lags as well, because that might happen as well if too many people switch to that. Okay, so let's keep moving. So essentially, sharing. Okay. So anyway, so where I was here is I was saying that after the LU instruction produces the result, right? So that result go all the way to either the data memory, or it can go to the register file, depending on whether the instructions want to store the results. So this is a very simplified data path, but you see there are different paths here possible. And this is something we need to orchestrate. So essentially, the question we will try to answer right now is what is happening when you run your executable. So we would really gonna look at when you run ls on your Linux machine, or you write your favorite game, what happens when you run. Okay. So what happens? The OS loads a bunch of instructions into the memory at a certain location. And CPU finds that location and executes the instructions stored one by one. So this is what happens at a very high level. So when I say instruction, you don't really know what it means. So this is how instructions really look like, right? It's really a sequence of zeros and ones and doesn't look particularly meaningful. So it looks like a very long 32-bit 4-byte binary string. So what we're going to do now, we're going to try to understand and decrypt what exactly information is stored here. Okay. So how do we remember the location of the current instruction? That's the first questions we need to understand. So that's the program counter. So that thing called PCO, the program counter, is a special physical register in your hardware that stores the location of the current instructions. This is the instruction that tells you where you are right now when you execute your code. So we, in most architectures, all instructions for simplicity are 4-byte long. So this means that if I want to go to the next instructions, we do typically +4 to increment the current PC location. So the questions I have for you, if I always, do I always can just do +4, or I need to be smarter than that? So is there any other cases where I need to change the program counter other than incrementing it by +4 if I execute instruction by instruction? Yes, so Joanne is saying if statements. Yes, remember there is control flow instruction that if there is a branch of some sort, so if you had if statement and I need to jump somewhere far, so I need to have a way to sometimes overload the PC, and that's done by branch instructions. I will talk about them in today's lecture as well. But otherwise, essentially, there are two possibilities for program counter. You either increment it by 4, or you overwrite its value by some other value through a jump instruction. So there is only two possibilities, right? And this is a part of the data path, you see. So the behavior, what we do for a program counter depends on the instruction, right? So by default, it's +4, but it might be different. Okay. So PC values can also be loaded, as I said, a result of a LU operation or jumps to a memory address. So here's the instructions. So the next thing the processor wants you is do it. And you're like, okay, what's I'm supposed to do with all of that? That's not particularly meaningful. So how are we going to read this? So the questions we want to answer now, what does the instruction really mean and what does it have there? So what operations can I do and where do I get the inputs? So this is the questions you should ask. What the instruction mean? What operations do I do with these instructions? And where do I get my input and where do I store my output? So this is the decode stage of the instruction. Remember, the first stage, we just read it somewhere, this string of zeros and ones. So how we do instruction decoding? The instructions themselves can be brought into small sections. That sections contain all the information needed to execute it. And that is known as the control word. For example, this is instruction. It's hard to believe right now, but there's actually an unsigned subtraction right now here. So how we do know there? So there's information stored there in certain parts of it that exactly encodes what the instruction is going to do. So the bits at the beginning, and in this case, the bits at the end, tell us exactly what we need to do. And I'll show you how I know this. So essentially, there are certain bits that are masked out that doesn't mean anything for these instructions. They store information about registers to use, but other bits are used for something meaningful. Okay, so essentially the information encoded here is tell me that that instruction doesn't deal with memory, just with registers. That's stored here. And if it's only registers, then this is the thing that stores the function, right? It stores the function I do. And this is the opcode that's stored somewhere that represent unsigned subtraction. And then to do the subtraction, what I need to know is where to store the data, right? And where to read the data from. And that's stored in specific registers here. So there is a source and destination registers, right? And I'll show you later on how to encode it. And if you do encode it, then magically you're going to learn that what says here, take register 7, so take register 0 minus register 1 and store it in register 7. So all this information is stored here. Okay, so how do we deal with instruction register? The instruction registers take a 32-bit instruction fetched from memory and reads the first 6 bits. The first 6 bits here in this instruction, they were all zeros, are known as an opcode, code of the operations, to determine what operations to perform. So essentially what happens here, the instruction register is going to take the 6 bits and going to look at what's in there. And then in parallel, it's going to read other useful information. It's going to read what operation to do and what are the parameters. So these 3 things encode different registers that I'm supposed to manipulate. This is register 0, this is register 1, and this is register 7, right? And we know because that, based on this opcode, that's supposed to be a minus unsigned, we know that that's a first argument, this is a second argument, this is the result. Okay. So opcodes are a humongous table. Here I'm going to show you a very simplified version of this table so that you get a feeling of it. If you ever deal and you're going to deal with real assembly, those instructions are much huge list data set. So there is like a big book manual from Intel that describes all the instructions and how they work. But at high level, things are relatively simple. As I told you, the first 6 digits of the instruction give you the opcode that determine the type, except for their so-called error type instruction that are marked in yellow. For those ones, their opcode is all zeros, and then there is a function, right, that stores at the end of it that tells you what to do. This is yellow instructions. So this is their last 6 bits of their functionality, right? The reasons why their opcode is zeros because they don't manipulate memory, so they need fewer bits to store, and you need to distinguish them with the similar instructions, but that manipulate with constants, right, or memory. So let me show what that means. For these opcodes, as I said, for yellow one, the opcode is zeros. For others, those opcodes, it's what you see here, right? And the difference between add and add-I, for example, you might ask, what's the difference? This thing just add registers. This one might also add a constant, right? And the constant require a lot of space in the instruction. So let me show you how the instruction look like, not in x86 architecture, but a much simpler MIPS architecture. So essentially, for a typical instruction, what you had a 6-bit opcode. Then there are 3 registers. So the registers for their 2 arguments and for destinations. So there is the first argument of the source, that's the second one, temporary, and that's a destination. And then there is a functionality here. But remember, there can be instructions that also deal with immediate values, right? Immediate values are constants, right? So this is when you want to add, say, register 10 to a constant 128. So you need to be able to write this, and this is the constants you can store. The maximum size constant you can deal with is 16-bit constants in MIPS architecture. And remember, some instructions might want to load and store information from their memory. So those instructions need to store the address, right? So the first category of instructions is called R type. The second one is called I type. And the third one is called J type, because that's, you're going to deal with some jumps, right? Okay. So I hope it's clear from high level what we're going to do with each of them. And now I'm going to do one by one and show you some examples. So to understand what is what, you need to read the first 6 bits. Then you know how to interpret that. Because you see, until I read the opcode, I don't know how should I interpret the remainder of the bits. Are they should be interpreted this way or this way or this way, right? So this is a challenge, right? Sometimes. Okay. What if I close the chat and open it again? Okay, any questions here? Okay. Does anyone understand how to figure out which instruction you have, R type, I type versus J type? So the question to you, how do I know that something is an R type instruction? Yes, the opcode, but what should I see in the opcode for R type? All zeros, right? All 6 bits should be zeros. Yes. And for I type and J type, they won't be zeros, right? They're going to be something meaningful there. And then by reading that, I would know how to interpret what comes next. Okay. Okay, let's move on. So we'll talk about R type first. So R type, not a big surprise, is a short for register type instructions because they operate only on the registers. And that's much simpler because there's no big constants to deal with. This instruction have fields for specifying up to 3 registers and potentially a shift amount if you need to do some shifting. These registers are 2 source registers, RS and RT. They're stored here, and 1 destination registers. Remember, because the number of registers is limited, and we know that in MIPS architecture, we typically have 32 registers. That means I just need 5 bits to store the index of the register. So I can represent 2 to the power of 5 different registers. So that's store me register index for the first argument, for the second argument, and that's for the output. Typically, if the fields are not needed, then the rest is coded with zeros. So for the opcode, for the R-type instructions, the first parameter is stored with all zeros, right? And the functionality is stored here, right? The question for you, and that's more like a brainstorming questions. Why would architects do this? Why wouldn't they store the functionality right into the opcode, right? Why would they, for register instruction, they store all zeros for the opcode and the actual functionality is stored here at the end, at the tail? Oh yeah, so sorry, I answered David's question. How do we differentiate I-type and G-type? So how do we differentiate? We just look at the opcode. The opcode that belongs to the J-type has only a few values, right? And we see those values later on. So we know that's a J-type, right? And you look at the opcode. But for R-type, the opcode is all just zeros. So my question is, why do you think or hypothesize why the opcode for the R-type instructions are all zeros and the real functionality is stored here, but for other instructions, the information about functionality is stored in the opcode? Yeah, there is very good rationale here. It's not the full answer, but it's a good first step to have more opcodes, right? Remember, opcodes is only have 6 bits here. So I can only store 2 to the power of 6, right? Which is 64 different opcodes that I might want to have way more different instructions, right? Especially if you want to cover all the different math. So for the most common instructions that I just operate on registers, I don't want to use those bits and limit other more fancy instructions. So I keep this functionality in here. So this is a part of the answer. So I want to save the opcodes. Another good thing is because every instruction is 4 bytes, these bits are otherwise not needed. There is another bits here to store all the relevant information. So I had spare bits so I can use them here. So that's a second reason. And the third reason is because those are the most common instructions, the ones done in registers, right? Your compiler is going to generate mostly those instructions. And for them, quickly decoding them is very good. So if you see the opcode zeros, you already built the circuit. So you know that detecting all zeros is very fast. So I can quickly detect all zeros and I don't need to do fancy decoding. I already know I need to read this. So I can very quickly detect all zeros, right? And I know how to read functionality. So there are multiple reasons. A lot of cases in architecture, the decisions are made based on multiple arguments, right? So here I want to save opcodes. We have spare bits for R-type instructions, and we can do this very efficiently. So all together make the architects build it this way. But the key thing I want you to remember, so R-type instructions are just pure registers. This is first argument, second argument index. This is output. That's another shift if needed. And that's the function, what you do, add, multiply, or subtract. Okay. So let's look at some examples. So remember this instruction, right? So let's go over it again. So first 6 bits, that tells us this is an R-type. Then we look at the last 6 bits because that's a functionality. So these bits here would tell us that's XOR instruction. And then we'll look at these 5 bits. This is 110. This is register 6. How about this guy? What's that register is? Anyone wants to try to answer? There's a question about shift amount. I'll cover that. Yeah. So another one is register 17. And there is this register as well, right? Register 5. So guys, wait about the shift, I'll talk about that. So essentially what's encoded here is I want to do XOR between register 6 and register 17, and I want to store this in register 5. That's what these, zeros and ones are storing, right? And that's another example. Again, the first 6 bits tell us this is an error type, and this is all zeros. And all zeros are a shift left instruction. And shift left instructions use that parameter. So someone asks, what is this shift about? That's what it is for, right? How much to shift. And then for shift, that's a registers, right? That's one parameter, and that's a second parameter. So left shift what's in register 17 by 12 bits and stores the result in register 5. And these bits are not needed, right? They're not utilized. Okay. Is this clear to everyone? So this is the way how you represent some constants when you manipulate with shifts, and shifts doesn't need the other register. That's the beauty of it. Okay, so let's look at the data path of the instruction. So remember there was the simplified data path overall that I show you. Now I want to show you with yellow, using a yellow color, how each particular data path is invoked at different periods of time. So for example, for error type data path, so what happens is for the most part, the function field tells the LU what operation to perform. The register RS and RT are sent to the register file. So what happens after I read the instruction, right? Because that's an error type instruction, it has to send request to register to read two of its register, right? So it needs one called RS with index RS and another one with index RT, right? And that's what you read from the register file. And then those goes through, the maxes, and then they come as a parameters to the LU, right? So the LU takes this parameter A and B based on the instruction stored here, and then it performs the function you want it to perform, right? Remember, we learned about LU, so we know which instruction it can perform, right? And then we had a register RD that is sent back to the register file to specify the location of the results. So here we take this path, right? We don't go to memory, we go to the max again, and then it goes back to the register file. So essentially maxes, demaxes really help us to read the relevant memory from the register file. And this is specific data path you're going to do for error type instruction. So if someone ever asks you, what is the data path for this instruction? This is essentially what you're showing. You're showing a sequence of steps, either in color or in plain text, on what's happened step by step. So you see, not everything is invoked all the time. Okay, so that covers the most simplest error type instructions. Let's talk about now I type instructions. Any questions before that? Oh, there were some questions here. So sorry, somehow it wasn't showing me. Like, let me answer all the questions here. So RS is ignored in the shift. How did you know that it was XOR that Ivy asked? So I know it was the XOR, but based on the function, right? So the last 6 bits, right, of the instruction tells me that's XOR instruction. So I had a table. Remember, I showed you the table at some point. That table tells me which function it is there, one of the yellow instructions. So if we go back there. Yeah. So if you look here, this opcode, right? That tells me that's XOR, right? Because it corresponds to both op and function, right? So each 6 bits are encoded in this table, and there is something that maps to each of this. Does it answer your question? Okay. So let's. Okay, so we went to that example. Yes. Okay. Another question, the function time was set to XOR, right? And then, I don't know the critics question, the last 6 bits tell you the function. Okay, I think that question was answered already. Okay. Let's move on. So this instruction have a 16-bit immediate field, right? Those I-type instructions. So how we know that they are I-type instructions? Again, remember the opcode. That's the one that were in white. And they called I because they had an immediate field with the big constant here. This field is a constant value which is used for, it can be used for an immediate operand. It can be used for a target of a branch, for example, branch if equal operation as an offset, or it can be an offset of a memory operand. Remember, if you want to do a load or store, I need to specify the address, and the address might not be perfectly stored in the register, so I might need some offset from the memory to have it from. So for branch target offset operation, the immediate field contains the sign difference between the current address stored in the PC and the address of the target instruction. What does that sentence mean? It means that here, I typically don't store the absolute address of the instruction. It's very difficult to manipulate those. What we have instead is the offset. So instead of having here the absolute very long instruction, we store something like 400 here. And that means that when you do a branch, you want to do PC plus or minus 400, right? And it's a sign value, right? So it can be both negative or positive. So it tells us where to branch from the current address. And that's the value we're going to overload in the PC. Remember, this offset is stored with the two low order bits being dropped because all the instructions are word aligned. Remember, when I talk about instruction, I told you that every instruction is 4-byte, 32-bit. That's a word alignment, right? You cannot have instructions start in the middle of the word. So everything always jumps at the granularity of 4-byte multiplied by some, integer value. Okay. So again, this is just show you what the word alignment means. So every instruction is a 4-byte, one word long. So the starting address of each instruction is always a multiple of 4. And then essentially this is how we see the offset. So for address 0, that's how you interpret. For 4, when you read when you interpret the offset, you don't look at the last 2 bits, similar to caches. Remember that offset doesn't matter. So 0, 1 means the address 4, right? And this is the bits you care about, right, when you do the offset. So the lowest 2 bits are always zeros because you never jump into the middle of instruction. So the question for you, why wouldn't you want to jump into the middle of the instruction? Any ideas? So why can I jump into, address 2, for example? What would go wrong if I do this? Well, Sam has the right idea, but I want a little bit more concrete. Yes, you're lost, but why you're lost? Right. So essentially, I had a very simple processor right now that I described to you that only knows how to interpret the instructions, and it expects a 4-byte values, right, to read and get all the relevant information. If I jump into the middle of the instruction, instead of the opcode are going to be somewhere in the middle, looking at the register numbers or something else, right? Or part of the constant. So I'm going to read completely bogus information. All that said, there are architectures where that's not prohibited, and some viruses or malicious code actually use those things, and they jump into the middle of instructions and they know how to write the constants that they look like code. So essentially, some viruses are essentially doing that. in the architecture that's not restricted. In an architecture we deal in here as a MIPS architecture, that's just not allowed, but in some other architectures it is possible. So yes, you can get lost essentially, and you can get lost because you don't know how to properly interpret. You will start to interpret the data, and most probably you will be in trouble. You're not going to interpret it properly. Okay, so let's see some examples of the instructions of the I type. So here's one instruction, and I know every time I show you a screen, they all look identical, right? Until you decode it, it doesn't look any different. But when you start to read it, you see the difference. So these opcodes corresponds to branch on equal. So if two values are equal, this is the offset on where to go. Remember, this is the way we interpret the offset. So you want to go to the offset 152, and that's registers you want to compare on whether they equal or not, registers 6 and register 17. So essentially this opcode instruction here corresponds to this thing. So if registers are equal, then I take the branch, right? And I change the PC. Otherwise, I go with the default version, which means branch is not taken, and I fall through and go to the next instruction. So essentially this instruction, the only side effect of it is the change of the PC. It doesn't add any registers, it doesn't multiply, it just doesn't change any flag. The only thing it does, it's rewrite the value of PC, okay? Okay, another example here. So we had this instruction that starts with 1 and all zeros, and that's loading a byte. Then that's a constant, that's an address. So right now we use this immediate value as an offset, and we interpret this as an address, and this is 38. And that's register 6, and that's register 17 again. But the trick here is how we interpret them. So this instruction means I'm loading from memory. So the memory has the addresses, so but the addresses are very large addresses, right? The memory is like 32-bit addresses. So the way I deal with that, I have the value of the register of the memory as an offset from some value. So I had register 6 having this value, right? And I then add offset of 38 as an offset from these registers. Why would something like that happen? Well, you can think about this as being a starting address of an array, and this is offset from an array, something like that, right? That's the best way to think about it. So this is the way we manipulate memory in their MIPS architectures, right? So we use one address as a base and the immediate value as an offset, right? And the result is then stored from registers. Remember, the instruction doesn't look complicated, but this is really a request to memory. Okay. So there is a question here from Jonathan. Why we don't add 2 zeros in the end of the offset this time? So this is because we interpret the that immediate value differently. Remember, I said that the branches, we cannot branch into the middle, right? The last 2 bits are irrelevant because we cannot jump into the middle of instructions. But in this architecture, I can read any byte, right? So the address can be anything, right? So I interpret the constant for the offset as just a constant, right? Because there's no limitation on being aligned to 4-byte. In reality, there might be some limitations as well, but here we assume we can load an individual byte, right? So there's no limitation. Yes, you're absolutely correct. It depends on the opcode. Remember, this immediate value, it's also up to interpretation. It looks as a sequence of 0 and 1s, but in each case, depending on the opcode, we can interpret it differently. For branch, it's one story. For load, it's a different story. Does it answer your question, Jonathan? How do you differentiate them? But you answer your question yourself by the opcode, right? I first see the opcode. I know it's a load. So my data path is going to take a different path and going to know how to interpret this constant, because it's that I need to interpret as a full-blown 16-bit value. In the other case, I know the last 2 bits I need to ignore. That's it. The opcode tells you, right? The opcode tells you how to interpret it. So you know that from the opcode that I need to have 2 registers, and like it's the same thing here. I know that register 6 is used in offset. I know I don't need to, and I know I need to access memory. How we know when to add 2 zeros given the opcode? We don't add. We just ignore the 2 bits. But essentially, because the opcode tells you you're now dealing with the branch instruction or with the load instruction. That's how you differentiate on what to do next. So if we are loading a single byte into a register, when does it load? Would it affect a single byte of register 17 or completely overwrite it? It's a very good question. There are rules about it in each architecture on what exactly going to happen, which I'm not covering here. But usually it means that all other information is wiped out. So essentially, if I read 1 byte, the other front-end bytes are 0. Usually, the architecture also has registers being interpreted differently. So when you're going to learn assembly in the next class, you're going to see that the same register can be interpreted as 1 byte, 2 byte, 4 byte, 8 byte, right? And it has slightly different naming conventions, right? So you can just tell you, oh, just write the first byte of this register, the second or 2 bytes of this register. Okay, and then you also, would it affect a single byte of register 17 or completely overwrite it? So essentially, the short answer is it's instruction dependent. So when you open the manual for that instruction, it tells you how exactly it's going to behave. Usually, it's going to just overwrite a specific amount of memory, right? But in some cases, on the MIPS architecture, it's going to wipe out the value, right? But on x86 architecture, you're going to have to deal with, in reality, they have different rules about loads, so they're not going to load individual bytes. The minimum you can load is probably like a word. So if it is a load op, when we just do it normally, if it's a branch op, then we add 0 to the offset. Yeah. So Jonathan, you got it right. Okay. So I think I would stop here for now, and then we'll continue in 8 minutes. Thank you, guys, and see you soon. Okay, sorry, can you guys hear me now? Okay, so I ask, please, can some people turn on your cameras? And let's continue. So essentially, we look at the I-type instruction data path, and there we have, as you can see, we only need one register, right, for the input. So we're going to read just one register here, but we would need to use a constant, right? So we use sign extended constant through the max, and those got into the proper LU instruction when needed. And then if we do any LU instruction, and then you maxed out and the results go into register file. So that's the difference. So this is a case of arithmetic instructions that goes, that deals with the constants. So what does the sign extension unit do? So remember, the immediate value we get from an I-type instruction is a 16-bit long, right? Why is it 16-bit long? Well, I don't have more space, right? My whole instruction is 32-byte, right? 32-bit. I can't really store 32-bit instruction in 32-bit constant into this instruction. But our LU unit are supposed to deal with 32-bit instructions. So I cannot just take 16-bit and feed into 32-bit, right? I need to do a sign extension. So essentially I fill in the upper 16 bits with the sign bit value. So if it's 0, right, then you fill it all with zeros. If it is 1, then what you get is those 16-bit ones up front. That's a sign bit extension, right? To convert a 16-bit constant into a 32-bit constant, okay? So this is just to remind everyone, because LUs we built are 32-bit LUs. Okay, that's what sign extension does on this thing, right? So, but this is just one example. If I deal with a arithmetic instruction, obviously there can be other cases. So, example number 2, if my immediate arithmetic operations will result in storing in memory, my data path is going to be different. So if that's the case, then what I do here, the same here, but the difference is here. Instead of writing to the max and back to the register, I'm going to write directly to the memory, and that's it. There is nothing that invokes here. Okay, so this is how the data path might be different for instructions belonging to the same type even, right? You would get this information from their opcodes. You're going to see whether they're supposed to load anything to the memory or they're supposed to store the results into the register. Example number 3, that's very different, is a branch instruction. So remember, the branch instructions are the one that manipulates with the address. So the instruction doesn't read anything from the register file. It just take the constant, it's just take the PC, right? And it adds the PC with the constant that you gave it. Remember the branches I show you were using relative addresses from the PC. So what they were doing is they were adding that constant to the PC. And then when this constant, and we use the same LU obviously to add up PC with this constant. And then we go through the max here and we update the PC, right, with the new value. Okay, that's what the branch instruction will do. Okay, so we covered more or less all the common cases for the I instruction. So the only instruction left are jump instructions. So the jump instructions are, there are only 2 of them. Jump, that denotes by G, and jump and link, called JAL. This instruction used the 26-bit coded address field to specify the target of the jump, right? So the questions I have for you, why do I need those jumps? Why can't you just use the existing branches? Any theories, any opinions? Yes, longer jumps. So if I'm gonna just use a small offset constant, right, 16-bit, I would kind of always stick to a very small segment, right? I cannot go too far. So I need long jumps to go to further addresses, right? But they are more, so essentially they're more rare. Like most of the cases where, say, within a loop, we don't even need that. So essentially this instruction used 26-bit coded address field to specify the target of the jump. The first 4 bits of the destination address are the same as the current bits in the program counter. And the bits in the position 27 to 2 in the address are the 26 bits provided in the instructions. So these bits at position 1 and 0 are always 0 since instructions are word aligned. So essentially the best way to think about it's the target of a jump that tells us where to go. Okay, so here's one example of that. So we read this instruction that says that's a jump. And then we take this whole blown concept. And this constant tells us where to jump for the PC. And then essentially PC jumps to their to the specific address, right? That's encoded here. So you don't need to remember any of that. That's all, you know, encrypted here. But that's the general thing that G-type instruction does. It takes the constant, it knows how to interpret the address, what to do with the bits, and then it jumps. So jump and branch instruction use the data pair similar, but they use it in a different ways, right? So that's something I want to highlight. So branch and jumps are conceptually very similar, and they use similar data path. If you look at what G instruction does, it has a very similar data path, right, to the branch instruction. The key difference is one is relative, right? The other one is absolute, right? So the absolute load an immediate value over the top of the old PC value. So that's where the difference is, relative versus absolute. Okay. So the key takeaway I want you to remember so the question is from Joan, the first 4 is the same as the first 4 of the PC. Yeah, so remember what this means, Joan, is essentially the program counter is 32-bit addresses, right? So, but the constants is only 27-bit, right? So it reuses 4 bits from the program counter, so it cannot jump infinitely, right, using this constant. So it reuses the bits from the program counter on the rest. So it's a long jump, but it's not an infinite long jump. So it takes the first few bits from PC and add a very long constant, but still it's not fully replacing PC, right? It's replacing most of the bits except for 4. Does it answer your question? We can technically store a 32-bit constant to represent any address just because the whole instruction is 32-bit, right? So we had to use different tricks like I'm showing you, right? Or are they all, so when I said one is absolute and one is relative, it's true, but even there, the long jump, like J instruction, still not completely, completely free. But they're absolutely random jumps across the whole address space are super rare. So there is a way to handle them through multiple instructions, but they're so rare, so it's not worth slowing down each other instructions dealing with longer addresses. So the whole point here is optimizing for the common case, not for a rare case. Okay, coming back to the lecture, so the key takeaway is different instruction flow in different data paths. And I hope after this hour, you remember what I mean by data path. You would understand what you need to write when you ask about the data path. So it's essentially the control flow into the graph of the execution. And one question I have here to test, thinking a little bit too, why don't I have any instruction that have 2 immediate values? So I show you 2 registers. I show you register plus constant immediate value. I show you like how to write into memory, but why not 2 immediate values? So why don't I have an add of 10 and 17 and write into register 0? Yeah, good answer, Juan. So yes, so that would be an extremely dumb instruction, because if you know both constants at compile time when the instruction is generated, any meaningful compiler should replace those instruction with a constant. So if you had 10 plus 17, the compiler, before generating the code for this architecture, should have been added that and generate your constant 27, and that would be replaced with a copy instruction, right? Like a move instruction into a register 27. So it's not there because it's redundant, it's not needed, and we don't want to waste of code for instructions that are not needed. Okay. So the next big topic today is a data path control. So I show you the data path. How do we actually control it? How is that achieved? So I show you which data path we take, but I now need to show you a little bit more details on how it's really done. So the instructions we're going to deal with are executed by turning various parts of the data path on and off to direct the flow of data from the correct source to the correct destination. So we kind of get what's need to be done in the previous hour by showing the right path, but now we need to know how it's going to be done more or less at the transistor level, at the signal level, how it can make a certain path happen. So what we're going to do, we're going to tell the processor to turn off the various components at the correct times. That sounds very complicated if you think about how we're going to do this at runtime. And there is a thing called control unit that does exactly that, that deals with a lot of different things that we're going to cover here. And this control unit takes in the opcode from the current instructions and sends signals to the rest of the processor. And remember, whatever is difficult for humans is easy for the processor, because it's a very tedious task, but computers are very good at it. So it's very easy to do it, to encode it actually. Within the control unit, there is a finite state machine that can occupy multiple clock cycles for a single instruction. And that control unit send out different signals on each clock cycles to make and nicely orchestrate the operation happening each cycle. So essentially the control unit sends signals through these green lines I'm showing on the circuit here, right, to various processor components to enact or stop them from doing different things. So we can tell the max to do something, like say read or write, depending on this signal, right? Source B, source A, and so on. So this is exactly how it operates. So for example, these two green lines, these goes into the max unit that then goes into our LU units, and they really can turn it on and off depending on what we want to do. So this is how we orchestrate. There is no real black magic here. You'll already learn about these control signals when we learn about transistors and how we build, say, register file, right? For example, this is a flag for register write, right? Whether one write or not. Remember, how we manipulate with register file depends on whether it's read only or write. So since that's important, there is a flag that we can put in to enable different data flow into the register file. And I show you that before. This is just combines it all together, and there's one control unit that orchestrates all these control flags. But each of these individual control flag we actually dealt before. There's no like miracle here. So this is essentially it. So there's this magic control unit that do all this magic and tirelessly working to make sure things happen at the right time. Okay, a certain combination of signals will make data flow from source to some destination. We just need to figure out what signals produce what behavior. And this is the tedious list of all of them. And I just give you a few examples, right? And you can look at the list later on. So essentially, there is obviously something called PC write. So which means that we write the LU output to the PC, right? Why we need it? Well, remember when we compute an UPC, right? Not just +4, but something more interesting for the branch. Then the result of the LU is needed. So we need to tell LU that that should go into the PC. That enables a certain path in the graph. So there are things like this. So for memory access, we want a signal that tells whether the memory is provided by the PC for instructions or LU for operations on the data. So we obviously need something like memory read versus memory write. So we need to distinguish between that. We also need to know whether the register file is receiving data from memory, but not from LU unit to take on a different data path, because that will be using different, signals into the maxes. Then there are things associated with the LU. For example, this is their signal for which operations doing the LU. Remember, our LU is fancy LU. It can do different instructions, right? So we need to signal which instruction to do, because it can do an add, it can do subtraction, it can use one register and a constant like +1, or can do something else. So we need to manipulate that. We need to tell where the source registers are going for LU. Again, we learned this flags before. There's nothing new about it here. This is just a description, right, on what happens here. Okay, any questions so far on this? Okay, I'll show you some examples, don't worry. So I'll just describe it here so you see what exists, and then you can practice on your own. So, and there is register write, registered and registered destination. So that's how to distinguish instruction providing their destination for a register write. Okay, so it looks still very complicated, I'm pretty sure. And that's actually a huge simplification from the reality, but I hope we can figure it out with a few examples. So this example is an instruction add I, right? That takes two registers, T7, T0, and 42, and that's used the notation you're gonna see on the assembly soon. So essentially, here I'm already setting up the flags that needs to be here. As you can see, most flags actually zeros here because you don't do anything fancy. The LU op is 001 because that's an add, right? And we had essentially a source register and a destination register to figure this out. So setting these signals will result in adding register T0 by 42 and storing results in register T7. So x86 has a different notation from how we store instructions. So the results goes first, and this is the first parameter, that's the second parameter, right? You're gonna learn this notation soon. But anyway, this is what happens, and we need to store right? So that's what we do. So we essentially give a register write of one flag, so we need to overwrite the results. So this is essentially a line of an assembly language, and then this controlling the data bar thing that what it does is essentially do step by step. So we implement the PC for the next instruction position. That's the first thing we need to do. So when we had an instruction like that, we have to take T1 plus 12 into the PC. And then assuming that the register T3 is storing a valid memory address, we fetch the data from that location in memory and store it in register T5. So how we're gonna do this on their MIPS architecture? We need to understand the role of each signal and what value they need to have in order to perform the given operation. So what's the best approach to make this happen? So the best approach is first figure out the data source and destination. That's the most complicated part. So you need to know where to send the data first. Then you determine the path of the data. And then you, based on that, you deduce the signal values that cause this path. So you really do what we did in the first hour. You find the right path, and then you find the trigger signals that are going to give us that path. So you start with like read write signals. At most, one can be high at a time. You cannot have both of them high, so it's relatively straightforward. Then you figure out the proper max signals along this data path, and then non-essential signals that doesn't matter that get an X value. So for example, here, if we want increment a PC, so if we want just do PC plus 4, given the data path above, what signals would the control flow unit need to turn to increment the program counter by 4? So let's look together. So first we need to find the program counter that gives us the source. So we need to get the PC, right? And we need also set a program counter as a destination. So we found the PC here, right on the graph. And then we determine the path for the data. So we need to get operand A for LU, the program counter. So what I really do, so remember here, I found it, right? First, I found my input, the PC, right? If I want to increment the PC, I need to take the PC first. Then the first thing I do is I found it here where it goes, right? Program counter. And I know I need to ship this PC to the LU. So this is my data path to get there, right? So operand A is PC. The second operand is the constant 4, right? So I need to feed the constant 4 in here, right? So this is a literal value 4. So that through the maxes that we need to, properly orchestrate has to go into LU unit. LU unit is going to give us PC plus 4, and then it has a max, right? So I need to take it but I don't want to go out there to memory, for example, right? I need to take the path that would let us bring the value back to the PC. So I go to this path to the max unit, and then brings me the new value of the PC back, okay? So this is how I found the right data flow path, right? That's what I want to do for this example. So how I make this happen? So I need to set up the signals for read and writes, right? So we follow the algorithm that I wrote you before. So we know that I want to write the PC at the end. So I want to say PC write as high, so equals to 1, and all others to low, because I override the PC at the end. That's read and write signals. Then the max signals. So let's look what kind of maxes we had involved. So we had a PC source is 0, LU source is 0, and LU source is 1 to activate this path properly, right? That's what's needed for those maxes to get the right results. Why those ones? Well, because here you have this max, and I don't want to read this guy, I want to read this guy. So this is why this is 0. Here, I don't want to read this value, I want to read the constant, right, for the constant path. So I use source B as 1. So that explains you what exactly is where for each max unit. And here PC source is 0. So this max unit, no, I want to take this value, not any other value, and that value goes into here. So it's really a very tedious process, but there's no black magic here, right? I really need to draw the flow I want, and then I go and write step by step each flag I need to make this happen. Okay, any questions here? We're gonna do more complicated examples, but that just shows you what's happening in the processor. Okay, all other values are like you don't care, either zeros or X's. So other signals for this data path, remember I was using LU, so I would need to set up LU op as 001, which corresponds, I just reminding you, remember when 2 lectures ago we learned about LU, so that corresponds to C in as 0, S1 as 0, and S0 as 1, which kind of gives us A plus B. And PC write condition is X when the PC write is 1. Okay. So this looks like an extremely complicated answer, but that's what you get at the end, right? So this is what you're gonna get if you're gonna do everything properly. And I just want to explain, you don't start to try to guess this answer, right? The way you do it is the key is build this data flow, figure out which exactly flow I need to take for things to happen. And each step is relatively simple. Because if I know I need PC, I need to add it up. I know I need to flow in this direction, and there's only one way I can get to that, right? Through this path, right? Because otherwise I'm going to get something wrong. And then I need to make these mocks to do what I want. I need to do this adds to do what I want. And then I need this result stored in the right location. That's it. And everything is done very similarly. So, so now let's try to do another example, and we'll try to do addition of R1 and R2 registers and store the result in the register R7. So this is what we're trying in this example. And again, I'm going to drive you through very slowly. So I expect you to ask questions if something is not clear. Okay. So this is instruction we are doing. Add R7, add R1 plus R2 into the register R7. So the first step, source and destination. Our story here starts not in the PC anymore, not in console. It starts in the register files because it's a register instruction, right? The first thing I need to do, I need to read values from a register. So the first thing is the data goes from the register block and then it goes back to the register block as the result. So I need this guy and I need this as a result. So the data needs to eventually come into the register file. Okay, how we can achieve that? So let's look together. So essentially, there are several things that needs to happen. So first, we need to determine the path of the data. Data needs to go through the LU before heading back into the register file. So essentially, I read one register here, one register here. That max needs to take the right value, right? Enable the right thing to pass it through. This max needs to do the same thing and pass it through, right? That goes into here. Then that results get out of here, but it doesn't go in this direction anymore. It goes through the LU output, and that goes all the way here. There is a max here that also, decides which input to take, and we know which input we need. So we take that input and then goes back into the register file, okay? And we also need to tell the register file that it operates in the right register mode. So we need to make sure that thing is enabled from here. Okay. So the register write flag needs to be high, right? And PC write condition, memory read, memory write, all these other flags would be low. Only register write needs to be high. Okay, everything else is low. Okay, most cases, most flags are low. Okay, the next thing is all the relevant max signals. So what are the relevant max signals I have to deal with? Well, obviously these two guys, I need to get this set to be 1 because I need to get this guy here, not this guy. And LU source B has to be 0, 0 to get you to here, right, to this guy. And LU op, surprise, surprise, needs to be an add. So that's encoded as 001. And then the maxes before registers, right? That has to be the one, this guy, right? That has to be 0, right? To get this value, not this value. And then irrelevant thing, everything that you're not writing to the PC. So PC source goes to X. No reading from memory, that flag go to X. So everything goes to X's, whatever is irrelevant. So at the end of the day, that's what we get. And that's the things that are important. Register write, those zeros here, right? That's what we get. And then remember these guys, these things associated with the compute unit, right? So, and this is just a side note about how to interpret register destination for different registers. Okay, so anyway, this shows you how you can get all this relatively complicated information in a straightforward manner. You just do it step by step, right? And the thing starts with the building data flow. As soon as you build the data flow correctly, the rest is a very straightforward process. Okay. Any questions here? I know that's not an easy material. Even in a very, very simplified form, it's not easy. So I was hoping to hear some questions here. Again, I just highlight this one more time. Remember, getting this path is the most complicated and the most important thing, right? And this is how the computer architects work. Like what they spend a lot of time is making this data flow to work. And after that, the process is relatively straightforward. So high resolution. So you can get the slides and you can make the resolution as high as you want, right? That's just PPT format. So you can make it as big as you want. So you can make it high resolution. On my screen right now, which I have a large screen, it's actually quite big. So you can make it any resolution you want. Okay, any other questions? Okay, so essentially, it took us 3 full lectures, but we really more or less covered everything your processor does. We look at the compute unit, we look at storage very carefully, and we look at the control today. So now, to be honest, you're at the place where you know everything about hardware at high level reasonably, that you can essentially build a processor. So essentially that's what the processor does. And the next few lectures, what we're gonna do, we are gonna learn the assembly language, right? And that's essentially the high level abstractions about instructions that tell the processor what to do, but the processor itself, we pretty much learn, right? So right now, when you look at your phone and you're looking at your computer, the brain of it, the CPU, you pretty much understand what it does, right? It's, even though there are some more complications to what happens in there, the basic stuff is pretty much the way we were describing it here. Well, we have this kind of questions in the final. I like those questions. I usually ask them, maybe. So it's, I will decide what to go in there. So yes, I spend a lot of time in there. So it's totally possible I might ask some questions. I don't know which level of complexity about this topic. So yes. And as you can imagine, you're gonna have, I'm talking about final, not the quiz. In the quiz, the question's supposed to be short to test your understanding rather than, meticulous knowledge. We can still ask questions on the quiz, but they're gonna be much shorter to answer. And in the exam, again, you can look at the diagram, right? It's all in front of you. Your examples are in front of you. You'll be just given a slightly different instructions. You would have to repeat the process, right? And just one thing to remember, when you're going to do the final, it's different from the quiz. So I need to see your thinking, right? So I want you to say, oh, don't try to write just the answer. Explain, like draw the data path. Say like, or if you don't want to draw it, you can just say, I need to enable this path, and this part, and that's why those signals are the way they are, right? So the explanation is helpful. So I want to see your thinking rather than just the correct answer. Okay, any other questions? And don't worry about the quizzes so much. You guys already perfect at quizzes. Like an average is like 90%. So I guess you master it. So remember, the quizzes are really not about getting high grades, and they don't matter a lot for grades. They're about you learning, right? So it doesn't affect your grade dramatically. What the hope is that you're actually it's gonna motivate you to learn, and you would understand things better while preparing the quizzes. Okay. Any other questions? Yeah, I'll talk to TAs. The project hopefully will be released in the next week. It's a good question. Also, one of my TAs really want to teach one of the classes, so I think one of the lectures will be taught by one of our TAs. So you get someone other than me, hopefully it's going to be more exciting. Okay, any other questions? It's going to be Mustafa. You had a lot of experience teaching the classes. Okay. Okay, any other questions related to logistics? Okay, so just to finish things up. So essentially, if you write some code and then it's compiled in C, Java, or any other programming languages, at the end of the day, what's going to be executed on, you know, on your CPU is the sequence of the zeros and ones called instructions, right? Computer doesn't understand anything else. Those zeros and ones are going to be interpreted the way we learned today. So essentially you write your, your code in your favorite language. Then there is a magic compiler that's going to go and generate the binary for you. Depending on platform, it can look different. But at the end of the day, Linux or Windows or Mac, it's a binary that's an executable file that has written those instructions in some a little bit more high-level language, like assembly language. But then this assembly language instruction, at the end of the day, they will all translate it to the sequences of zeros and ones. There is nothing else that computer understands. Those zeros and ones then going to be, interpreted in a fancy way, right? The way we described today. And we're going to learn exactly what you're supposed to do and where to go after each instructions and what to manipulate. So at the end of the day, at each stage, we're doing something super primitive, but that allows us to build a very complicated projects right now, right? So pretty much any executable run on your operating systems, what it does, it takes this binary, it has a way to load it, right, from the memory into the instruction memory, right? And then it sets the starting PC to the beginning of your code. That's what the operating system does. I understand you didn't have an advanced course on operating systems yet. That's something you're going to learn in C69. But that's the basic thing you need to know about the OS goal. Was take this binary, it loads it, and then it sets the PC to some right starting position. And that starting position, surprise, surprise, is the beginning of your program, the beginning of your code, right? The beginning of your main, right? If you write a C code. And that's where the whole process starts. And after that, the whole control flow is given to your program, and the OS just runs in the background, making sure you don't break anything. But the code is then executed by your program. And then CPU job starts by loading instruction by instructions pointed by the PC. Remember, at every stage, we either do PC plus 4 or we branch somewhere. So every time we know where to go next, right? Up until we're done with the code. And at the end of the day, we do some return and exit from the program, and then the program is done, and then OS is going to load something else, right? The OS has the way to decide what to do next, which you're going to learn in a different class. But from the CPU perspective, its job is done. It's loaded your program, it's executed instruction by instruction. At the end, the results are stored in registers and memory, and that's what you care about, right? And that's pretty much it. And the way magic happens is the control unit checks the opcodes, those instructions, the first 6 bits, decode the rest of the instruction, and send signals to set up the data path. One thing I want to remember, I picked the simplest possible architecture, MIPS architecture, to explain you how it works at the bottom. x86 architecture that's used in most of your PCs, right, will be different, but not dramatically different. It's just more complex, but it's fundamentally the same. It's just the opcodes are longer, right? There are more bits for registers and things like that, but there are no fundamental differences, right? It's pretty much identical in that sense. So essentially, all of that, all this control flow logic is actually taking billions of MOSFETs, doing switchings of on and off. And that's essentially everything you learn fits all the way to a nice, I wouldn't call it simple, but nice, elegant design. So data flow through the data path and electrons move around. So at the end of the day, if you want to do a hello world, it's what's going to happen. There is going to be plenty of those things involved, billions of transistors involved just to print a hello world for you, okay? That's a full story of what's going on. And the next thing you need to start learning is the language that the processor understands, and try to write and do some interesting projects with it. Okay, so any questions? We had around 9 minutes left, so I'm happy to answer any questions. Oh, Sam, you're asking really good questions. I wish I could spend more time answering them. So how much performance improvement can instruction set have? So it's a very hot topic around 20, 30 years ago, where people tried to build different instruction sets. So to explain to everyone who doesn't know about things, instruction sets is that intermediate language your assembly is written into, right? That's the language that the CPU understands, and that's the language you talk to it. So instructions can be very complex or very simple. And whether one is better or not, there was a debate by researchers for like 2 decades. So there were people that were proponents of a very complex instruction sets. That's what your Intel instruction is. That's why you open Intel instruction manual. This is like several thousand pages of explaining each instruction and different flags. That's Intel strategy. There were other people that thought that's a broad approach, and they were proponents of a very simple architecture. That's called RISC architecture. And in this architecture, everything can fit into a single screen with all their complexity, but it has their other downsides, right? So, so essentially, the short answer is what's better, what's not, depend on the use case. So your essentially, your phone most probably use a very simple architecture like RISC-like architecture, while your desktop is using more sophisticated architecture. Okay, but that's a whole lot of a different topic that's very research oriented. So we can talk Sam offline if you want to learn more about that. That's something usually covered in the computer architecture class, which is taught in computer engineering department or in advanced, more advanced grad level classes. I talk about this in my computer architecture class for grad students. Okay. So I think someone asked about the project, and I think there's already posted an answer. So essentially from the previous years. So we're gonna do something similar, yeah. Can we get into NVIDIA after finishing this course? That's definitely not enough. So if you want to impress people in NVIDIA, you would need to get way more courses and you know, excel at them and learn things like CUDA probably, not just the basics. Yeah. Any other serious questions? All the details about the project will be released soon, Glenn. So we'll tell you. I think they're typically done in the groups. We'll talk about that. Any other questions? Okay, then thanks everyone. So we'll share the slides as usual after the class and the videos as well. Thank you guys. Sorry for the issues with the internet. That's very sporadic. So sometimes you work the whole day and it's fine. Thank you guys. Bye.